So what we're doing is we're going to think about the energy of things that are rolling. In general, that kinetic energy is from two things. There's the motion of the center of mass. This is what we already know. And there's also the fact that the sucker is spinning as it rolls, and that's going to be 1/2 I omega. So this is kind of linear kinetic energy, and this is rotational kinetic energy. We'll have to label that. These lectures are going to be much more fun because I bought a whole bag of colorful markers. Yes. Okay, so we've got linear and rotational kinetic energy, and in principle something could be rolling, and in that case, if it's rolling without slipping, for instance, then it has both of those forms of energy. So let's specifically get into that. If it's rolling without slipping, that special case that we really love, rolling without slipping, means that omega, well, remember that V is omega times ara if it's rolling without slipping. So we can look at this equation and we can change it just a little bit. I'm going to substitute in orange. Yeah. So I'm going to say that omega is V over r, and I'm going to take that and plug it into this equation up here and rewrite it, and we'll find the kinetic energy of an object that is rolling without slipping to be 1/2 mv square plus 1/2 I. Now I've got to square that. That's V square over R square. And I see some interesting structure coming out of here, so I'm going to write another equal sign and say that this must be, well, I guess it's 1/2. Ooh, what if I factor out a 1/2 mv squared, the traditional kinetic energy of the object? Then the first term is just 1. And the second term, this is a little bit more complicated. It doesn't have an m. So since I divided by m, I'm going to have an m in the denominator. And it doesn't, well, see, it's got an r squared down here too. It's got an r squared down there. And v was factored out, so that's not there anymore, but there's still an I. So check my math. I hope you'll find that this is the case. This is interesting because this is the linear component now, and this is the rotational component. And so those two forms of energy are present in a very interesting way. I want to write this equation again, and I want to think about what it could mean. We are saying that the kinetic energy of an object rolling without slipping is equal to 1/2 mv square times 1 plus I over mr square. Interesting. I is this moment of inertia, rotational inertia for an object. So we could label it as such, rotational inertia. Do you remember the forms of I that can be present though? I remember there was some object that actually had I for something. We had I is equal to mr square. And that's, ooh, what was that? Oh man, I don't remember the last lecture. Maybe you should go watch it again. No, seriously, I remember it. You don't remember it. You go watch it. So this is m times r squared. This is the case for a ring, or a loop, I guess those are two names for the same thing, or a single mass on a massless stick, like that apple that we had in the previous video. So for a ring, a loop, or a single mass on a massless stick, we get I is equal to mr square, and so then this equation becomes, ooh, look at this. This equation becomes simply K rolling without slipping for a ring becomes 1/2 mv squared times 1 plus, I is mr squared, and we're supposed to divide that by mr squared. Well, that's just 2. We've got 1/2 mv squared times 2. So the kinetic energy is doubled if something is rolling without slipping and it's a ring or a loop on I mean, it's hard for a single mass and a massless stick to roll without slipping. But for a ring and a loop, what this says is that half of the kinetic energy of the system is the fact that the center of mass is moving. And the other half of the kinetic energy of the system is the fact that it's rolling, that it's rotating. Okay, so we've got center of mass motion and rotational motion corresponding to these kinetic energies. But let's go back up to this equation right here, because not every problem will have a ring or a loop. If you look at the table in our book that shows the different moments of inertia for things, the greatest it ever can be, and I'll put this in a little box right here, I is less than or equal to the mass of the object times the radius of the object square. Sometimes it's much less than that. Sometimes, for some configurations, it's even like 1/12 the mass times the distance of the object. So we're talking about this as an upper bound. That means that the greatest contribution to the overall energy of something rolling without slipping, the greatest it can ever be, is half rotational and half translational. But if you have a different object, let's say a solid disk, if you have a different object, then it's not nearly half. And we'll work that as a problem in class. Don't worry about that sucker right there. No, worry about it and get concerned, because we are going to work it. So let's take a typical problem where you've got a hill and you put a can of soup up on top of the hill. It's Campbell's, right? And the can of soup has some radius r. Nah, let's put a ball up there. Let's put a lacrosse ball up there. And it starts up at some height h, and it's going to lose its energy, and at the bottom it's going to be rolling without slipping, so there'll be a little bit of this kind of stuff going right here, and there's also a little bit of this stuff going right here, and we know that V is actually equal to omega times r, because it's rolling without slipping. So I'll label this. Rolling without slipping says that that's true, and we can do some calculations about energy. First of all, when it gets to the bottom, it's going to, well, we can do some Mia's math. Let's do it. The initial mechanical energy is the final mechanical energy. Initially, we've got mgh, starts at rest at the top of the hill. Finally, we've got the kinetic energy. And the kinetic energy has this fun form, 1/2 mv squared times 1 plus I over mr squared. All right? And we probably want to solve this for how fast it's going, right? You thinking what I'm thinking? We could solve this for how fast it's going. And a little bit of fun algebra yields, ready for it? The masses cancel out? Do they? Do the masses cancel out? Do this algebra. You get V is equal to the square root of 2gh. Who's ever seen the square root of 2gh before? Yeah, it's not that simple though. 1 plus, down here, I over mr squared. So here's the thing. It depends on the moment of inertia whether this is going to be just the standard root 2gh. So how could we get this to be root 2gh? Well, I guess if I were 0, then this would be root 2gh over 1, and then we'd have root 2gh. What does it mean? I equals 0 means what? Oh, well, if I, let's see if we can get a definition of I here. It starts from thing 1 to thing n, and it's going to be a mass of each thing times the distance of each thing from the center. If this is 0, either we've got no mass or we've got no radius. So something with a radius of 0 would be a point particle. I equals 0 implies point particle. And until today, that's all we've ever considered rolling down a hill, because all the energy is translational when it gets to the bottom of the hill. But since we now have some of the energy as rotational, we need to be a lot more careful. And the velocity, you can see, if it's not root 2gh, it's going to be less than root 2gh. This denominator, the denominator decreases V, because it's going to make the denominator bigger in here, and so the speed is going to be lower. And I guess the larger I is means the smaller the velocity is at the end. Because more of the energy, for a larger I, a greater fraction of the total energy initially is going to be converted into translational kinetic. More of the energy will be converted into rotational kinetic in this term right here. If I is very small, then all the energy can be in translational kinetic, but if I is very big, then more of the energy will be in rotational kinetic. Again, only up to a factor of a half. The greatest it can ever be is half the energy is translational and half the energy is rotational. So I'm about to show you a race between a ring and a disk. They have equal mass, and I showed my class this, and every person predicted the wrong outcome. Would you like to predict the following challenge? I'm going to give you a three-dimensional ramp. I'm going to put a ring on top of it, and I'm going to put a solid disk on top of it. They have equal mass, identical radii, and I'm going to let them go, and which one do you think will win? You need to decide based on what you've just seen before you continue watching. So, pause. Roll it. So we've got linear and rotational kinetic energy, and in principle something could be rolling, and in that case, if it's rolling without slipping, for instance, then it has both of those forms of energy. So let's specifically get into that. If it's rolling without slipping, that special case that we really love, rolling without slipping, means that omega, well, remember that V is omega times ara if it's rolling without slipping. So we can look at this equation and we can change it just a little bit. I'm going to substitute in orange. Yeah. So I'm going to say that omega is V over r, and I'm going to take that and plug it into this equation up here and rewrite it, and we'll find the kinetic energy of an object that is rolling without slipping to be 1/2 mv squared plus. So what we're doing is we're going to think about the energy of things that are rolling. In general, that kinetic energy is from two things. There's the motion of the center of mass. This is what we already know. And there's also the fact that the sucker is spinning as it rolls, and that's going to be 1/2 I omega. So this is kind of linear kinetic energy, and this is rotational kinetic energy. We'll have to label that. These lectures are going to be much more fun because I bought a whole bag of colorful markers. Yes. Okay.